Recent unexpected events have prompted NASA to enter a heightened monitoring status. For weeks, astronomers have been tracking the interstellar object designated 3I Atlas, meticulously observing its gradual movement deeper into the inner regions of the solar system. Initially, all indications pointed to a stable trajectory. However, almost without warning, ultraviolet detection data revealed a dramatic and significant surge in Hydroxyl low H emissions. Hydroxyl is an identifiable product of water molecule dissociation, formed when solar ultraviolet radiation breaks down water molecules. Its abrupt increase signaled a drastic change in the object's water release rate. Initially, the research team attributed this anomalous signal to instrument calibration errors. At a distance of nearly 3 astronomical units from the Sun, the theoretical possibility of a comet releasing such vast quantities of liquid water seemed implausible, yet the signal's intensity continued to grow, exhibiting a stepwise progression until observers became convinced they were witnessing an extraordinary astronomical event. Multiple observatories subsequently reported intense and sustained material eruptions, far exceeding expected characteristics for such a distant celestial body. One researcher vividly likened the phenomenon to a fire hydrant bursting open in space, a phrase that rapidly spread throughout the scientific community due to the lack of more plausible explanations at the time. Although NASA has not issued an official statement, the agency has swiftly implemented internal measures, elevating routine monitoring to a high alert level. The abrupt surge in liquid water loss rate suggests significant alterations within the interstellar object's internal structure, a phenomenon among the most challenging to predict precisely in astrophysics. Even more perplexing is the phenomenon's atypical initiation. It exhibited neither gradual acceleration nor progressive brightness enhancement, and lacked the transitional phases typically preceding major cometary outbursts. 3I Atlas appears to have instantly transitioned into a novel state of activity, as if long minus accumulated internal pressure beneath its surface had been abruptly released. Scientists are meticulously examining the original observational data to comprehend the phenomenon unfolding before them. Is this merely a transient outburst, or the beginning of a more grand celestial evolutionary process? The only verifiable fact, however, is what troubles researchers most. 3I Atlas is losing water at a rate far exceeding current physical models. Predictions for a comet at this distance from the Sun. Until NASA determines the root cause, the future remains uncertain. What troubles scientists is not only the total amount of water loss, but its specific location. At approximately 3 astronomical units from the Sun, solar radiation intensity is insufficient to trigger such intense sublimation. Typically, comets at this distance emit only faint, diffuse gas plumes. Their surfaces remain relatively cool, with icy layers usually shielded by thicker insulating material. Yet 3I Atlas is ejecting water molecules at a rate of approximately 40 kilograms per second. This data has been confirmed by observations of hydroxyl emission lines from multiple observatories. At such a distant location, the intensity of the water vapor stream should be extremely weak, theoretically approaching zero. The presence of hydroxyl serves as a crucial tracer. When ultraviolet radiation breaks down water molecules, it leaves distinctive spectral signatures. The expansion of these spectral signals around the celestial body indicates this is not a minor water vapor, but a powerful and persistent water flow. All this occurs while the object receives solar energy far below one's solar constant, with this energy only fully manifesting during the later stages of its orbital journey. From the perspectives of physics, chemistry, and thermodynamics, this observational data deviates significantly from existing theoretical models. Ejection phenomena of this scale point to only one possibility. An internal driving force within the object is expelling water molecules outward, potentially stemming from internal pressure, violent structural fractures, or suddenly exposed ice reservoirs. If this were a common cometary activity pattern, we should observe similar phenomena on other distant objects. Yet this is not the case. Comets within our solar system do exhibit firehose-like outbursts, but these are typically confined to regions closer to the Sun, occurring only when deep-seated ices begin to violently sublimate. The current situation with 3I Atlas is the exact opposite. Solar radiation is too weak, ambient temperatures are too low, and the extreme distance makes natural sublimation processes utterly incapable of explaining the observed phenomena. Even seasoned comet scientists acknowledge this level of activity completely exceeds the predictions of existing thermodynamic models. Each new puzzle, each observation contradicting current theory, points toward an unsettling conclusion. 3I Atlas's surface behavior fundamentally diverges from what we would expect based on our current knowledge. To understand why this outburst has perplexed scientists, one must first grasp the fundamental nature of 3I Atlas. It is not a young comet originating from our solar system, but rather a wanderer roaming through interstellar space. It is only the third object confirmed to possess this nature body that has drifted through the interstellar medium for approximately 700 to 1.4 billion years. This prolonged interstellar journey alone renders it fundamentally different from any object formed within our solar system. While typical solar system comets spend most of their lifetimes safely nestled in the cold, distant fringes of our solar system, 3I Atlas endured unimaginably long periods directly exposed to the intense radiation of galactic cosmic rays in the vastness of interstellar space. These high-energy cosmic rays can reconstruct molecular structures of matter, atom by atom. Over billions of years, they gradually eroded lighter elements, reshaped the microscopic structure of the icy layers, and formed a dark, dense, and nearly rock-hard outer shell around the comet nucleus. Estimates suggest this shell could be 15 to 20 meters thick, far exceeding the crust of comets, heated only by conventional solar radiation. This implies that 3I Atlas's frozen core must be so thoroughly encased within this thick armor layer that sunlight can scarcely penetrate it effectively at a distance of 3 astronomical units. Under normal circumstances, its internal water body should remain completely sealed until the object significantly approaches the Sun. Its immense size further complicates this mystery. 3I Atlas is substantially larger than Mu MUA, the first confirmed interstellar visitor, and even exceeds the size of Borisov, the second interstellar object. Such massive interstellar bodies are extremely rare in themselves, and the existence of one retaining substantial water resources after billions of years of interstellar travel seems virtually impossible. Cosmic rays should theoretically have destroyed nearly all available ice over such an extended timescale, leaving only dry, carbon-rich material. Yet 3I Atlas defies this expectation. It is neither dry nor tranquil, but instead exhibits pronounced instability. It suddenly erupts water, as if a high-pressure valve were abruptly opened. This is precisely the aspect deeply unsettling to researchers. The expected structure of 3I Atlas suggests it should effectively resist water loss at such great distances. Yet our observations reveal the exact opposite. The intensity of this outburst rivals eruptions typically seen in comets much closer to the Sun. This hints at deeper structural changes occurring within its core. If the hard shell formed by cosmic radiation has indeed fractured, the material concealed beneath may be far more abundant and volatile than previously anticipated. Should 3I Atlas continue losing water at intensities typical of near-Sun comets, this would unequivocally indicate sudden, violent changes beneath its surface. The primary explanation currently proposed by scientists is both simple and unsettling. The ancient shell may have fractured. After 7 to 14 billion years of cosmic ray bombardment, theoretical calculations suggest the comet's outer shell transformed into a super-hard layer approximately 15 to 20 meters thick. This shell acted as natural armor, effectively sealing internal ice layers and blocking heat transfer to deeper regions. However, this armor may have fractured under some unknown force. Once cracks appeared, the long-accumulated internal pressure could only escape through a single pathway, The sudden rupture of the ancient shell, akin to a bursting high-pressure valve, instantly released immense energy. As sunlight struck the newly exposed inner ice layers, water ice rapidly sublimated into water vapor, unable to vent effectively. The internal pressure violently erupts outward through the weakest fissures, creating the powerful water jets observers describe as rivaling cosmic fire hydrants. Laboratory experiments on irradiated ice layers also confirm once cracks appear in the ice shell, its dehydration level can skyrocket from near -0 to explosive levels in an extremely short time. This perfectly explains the violent fluctuations in hydroxyl signals. There is no gradual buildup, no prior warning signals instead. It activates instantly and reaches maximum intensity. This scenario also reasonably explains why the ejecta consists almost entirely of water rather than other volatiles like carbon dioxide. If the crack extends deep enough, it might even open a layer of pristine material never exposed since the body's formation. These internal regions may preserve primordial water ice, shielded from cosmic ray erosion for billions of years. Such a fissure would release gas streams fundamentally different from vapor, produced by externally exposed material already altered by cosmic rays. In essence, this offers a direct opportunity to observe material older than the Sun itself. However, the fissure hypothesis also raises new, unsettling questions. Why did the fissures appear precisely at this moment? Why are they located at such a specific distance from the star? Why is the force of the eruption so immense that it can tear through a barrier layer theoretically capable of breaking only under extreme heat? Even more puzzling is the fact that the water columns exhibit persistent eruptions rather than brief outbursts, suggesting the fissures are not merely surfaced airs but standing deep into the comet's nucleus. If this were the case, the internal water ice reserves fueling the jet would be extraordinarily vast. While a single fissure could explain the immense power of the jets, it struggles to resolve a deeper contradiction, the significant discrepancy between the theoretical thrust generated by the jets and the actual observed motion of the celestial body. If Comet 3I Atlas is indeed ejecting water at a rate of approximately 40 kilograms per second as observational data suggests, such a powerful jet should generate considerable momentum. The outgassing process itself generates thrust, following the same physical principles as rocket propulsion. When a comet ejects material in one direction, the law of conservation of momentum dictates that it accelerates in the opposite direction. Under such powerful gas flow, this thrust should be easily calculable, predictable, and leave a clearly discernible imprint on its flight path. However, researchers have not observed this expected phenomenon. The acceleration curve of 3I Atlas does not align with the theoretical thrust calculated based on the water ejection rate. Even when accounting for the loss of other gases like carbon dioxide previously recorded, the final momentum vector still exhibits unexplained deviations. Some observed motions aligned with model predictions, but by no means all. It is precisely these unexplained portions that have transformed into a new and more perplexing puzzle. The discrepancies between the trajectory diagram and the calculated results are what most unsettle mission engineers and orbital dynamic specialists. The intensity of the jet is undeniable, yet it fails to produce the directed thrust predicted by the laws of physics. Certainly, plausible explanations exist for this discrepancy. For instance, the orientation of internal fractures might form unusual angles, deflecting the thrust direction of the jets. Alternatively, the nucleus's surface rotation could cause the jet effects to stretch in different directions over time. The outer rigid shell might also act like a conduit, expanding or contracting its aperture as the core heats, thereby influencing the jet's shape and direction. However, even after meticulously simulating all these potential scenarios, researchers are left with a persistent sense that observational data, the existing models, fail to align perfectly, leaving gaps in the complete picture. Moreover, the longer the eruption persists, the more pronounced this discrepancy between theory and observation becomes. This contradiction becomes even more profound when considering that the water outflow is not a brief burst, but a sustained and steady phenomenon. Observational data indicate the jet maintains relatively stable and robust intensity, suggesting it should produce smooth, uniform, and predictable acceleration. Yet, the trajectory of 3I Atlas appears slightly irregular, as if the forces acting on the object are changing at a rate exceeding what standard cometary activity would predict. Some scientists have drawn parallels between this phenomenon and certain anomalies previously observed around comets. Perilhan points anomalies equally difficult to fully explain through simple natural laws. This does not imply the current phenomenon is unnatural, but rather suggests nature may operate in ways we have yet to fully comprehend. The powerful water jets, which should simplify celestial dynamics, have instead made them more complex. As the comet currently moves behind the solar disk, obscured by the sun's blinding glare, no one can accurately determine whether the thrust generated by its outgassing is changing over time, whether it is gradually increasing, decreasing, or being masked by deeper core activity. Scientists currently possess only the following verifiable data. The degassing phenomenon is real, water loss is substantial, and the observed acceleration values still deviate significantly from theoretical predictions. It is precisely this gap between theory and observation that has prompted NASA to significantly elevate its monitoring level for 3I Atlas. This unresolved contradiction has captured the intense attention of the scientific community. Within the 3I Atlas celestial body, there exists some stubborn factor that current models cannot explain. Now, all the perplexity, all the unresolved questions, all the conflicting data converge at a pivotal moment. The instant 3I Atlas ray emerges from the blinding solar glare. At this very moment, as it transits the sun from Earth's perspective, we find ourselves in an observational blind spot. No optical telescope can directly observe its form. No ultraviolet spectrometer can precisely measure its chemical emissions, and no instrument is currently positioned to directly monitor its activity. The most intense phase of this object's activity unfolds in darkness. Only when it reappears will we understand what transpired during this critical period. Scientists are primarily monitoring changes in its coma. If the water outburst was triggered by a temporary structural fracture, the jet's intensity should gradually diminish, accompanied by a decline in hydroxyl signal strength, ultimately restoring the comet to relative calm. However, if the outflow continues to intensify or new eruptions emerge, it would indicate that the fracture has penetrated deeper than previously anticipated, potentially breaching layers of material untouched for billions of years. In such a scenario, outgassing could become more violent, radically altering the comet's structure and exposing primordial material that has never seen sunlight. Next, scientists will closely monitor its color and brightness. A sudden shift toward bluer spectral tones could indicate the eruption of ultrafine dust particles or ice crystals from deep within its mantle, potentially signaling significant disruption of deeper structures. If its spectral curve remains relatively stable, this would more strongly support the earlier hypothesis of a brief, localized outburst. Subsequently, they will conduct a comprehensive comparative analysis of the total dust mass, and average particle size, and light scattering properties. This data will be meticulously cross-referenced with observations from before the comet's invisible phase to decipher potential changes within the nucleus during its obscured period. However, the most critical test will be the flight trajectory of 3I Atlas after escaping the sun's gravitational influence. If the thrust generated by the outgassing aligns with theoretical calculations, its trajectory should stabilize and follow a predictable curve. But if outgassing persists and its acceleration again exhibits unexplained anomalies, we will witness the emergence of a novel astronomical anomaly, one that cannot be explained by known mechanisms like simple outgassing, crack formation, or localized accumulation of volatile materials. This marks a critical moment where existing natural models face severe testing. Either these models will withstand scrutiny from new data, or they will begin to unravel under the pressure of fresh observational evidence. For a celestial body older than the solar system itself, This moment holds profound scientific significance. 3I Atlas has already shattered many of our prior expectations, posing serious challenges to existing thermodynamic models and exhibiting peculiar behavior not typically associated with distant comets. In the coming days or weeks, the cosmos will reveal the latest developments concerning this interstellar visitor. Will its outburst activity gradually subside, persistently intensify, or evolve into even more extraordinary phenomena? The observations after its solar flyby will ultimately determine the next chapter of this captivating cosmic tale. Regardless of the state 3I Atlas returns in, one thing is certain: we are witnessing an astronomical phenomenon never before observed by any living scientist, and the story of 3I Atlas is far from over.